In section 9.2 on understanding interest, we'll be studying interest rates and how to calculate both simple and compound interest. There are two terms that we will regularly use, the first of which is interest. Interest is the amount of money paid by a financial institution on a certain amount of money that you deposit. Or if you're borrowing, it's also the amount of money that you pay to a financial institution in order to borrow a certain amount of money. The second term, principal, or what we'll often call the present value. The present value is the amount of money that you deposit or borrow. There are two types of interest received from accounts of deposit with financial institutions or else incurred if you're taking out a loan. If the amount of interest is only based on what you borrowed or deposited for a fixed period of time and is not affected by the periodic payments made toward the amount owed if you're taking out a loan, or the periodic interest payments that you receive if you're depositing money, then that interest is called simple interest. It might help to make a simple example and just look at this visually. Suppose we take an extreme example of taking $100 and getting 50% in. That's very extreme, but it'll just help us figure what's going on. If you do that, in year one, you will earn $50 in interest on the $100. That's 50%. In year two, you will earn another $50. In year three, you will earn another $50. A good way to think about simple interest is that in a simple interest account, the interest that you receive on the principal doesn't earn any interest itself. In other words, only the $100 that you put in originally earns interest. Probably the easiest way to think of that is that you just get the $50 back yourself. It's not sitting in the account further earning interest. But most accounts are such that the interest received or paid, if you're taking out a loan, is factored in. In other words, the interest you pay is added back to the initial deposit and the interest begins to earn interest. Or if you're doing loans, the interest owed is added back to the total amount owed and begins to incur an interest charge of its own. The visual representation for simple interest is sort of flat. You get the same amount every time it's paid. But look what happens if you do what we're going to call here compound interest. This time, that $100 principal, and still sticking with a 50% interest rate, just as an extreme example, if you look at that, in the first year, that $100 deposit would earn $50 in interest just like it did with a simple interest account. But here's where it diverges. In the second year, that $100 would earn another $50. In the third year, it would earn yet a third $50. But that's not the end of the story, because the $50 that you earned in year one now begins to earn interest itself. So if it's $50 in year two, it will earn its own 50% interest, which is another $25. So you'd earn another $25 in year two. And that amount would earn another $25 in year three. And as you can see, as you move forward, not only is the principal earning interest, the interest itself begins to earn interest. And that's the idea of compound interest and how it differs from simple interest. Just sort of a visual to give you an idea of the basic difference between simple interest, which I think of as flat, and compound interest, which has this what's sometimes called an interest trajectory. You can see how that plays out. As I said, this is called compound interest as opposed to simple interest. The formula to calculate simple interest is I equals PRT. I stands for the amount of interest. So like in the first example we used, you earned $50 in interest. The I would be the $50. P is the principal, or what I like to call the present value. That's the amount you start off with. Small r is the interest rate expressed as a decimal. This is often referred to as the APR, which stands for annual percentage rate. So sometimes that little r is called APR. And T is the time, but it's always expressed in years. Don't forget that. Let's take a simple example. Suppose we have $500 that's deposited in an account that pays 6% simple interest. How much interest will be in the account in 4 years? Or another way of saying that, how much interest will the deposit earn in 4 years? It's a simple application of the formula I equals PRT. So write the formula down and plug in. The principal is what you start with. That's the $500. That goes in. The R is the interest rate written in decimal. That was 6%. Change it to a decimal, 0.06. And then it's multiplied by the time, which is 4 years. And do the calculation. So do 500 times 0.06 times 4 equals, and you get 120. So the $500 deposit will earn $120 over the 4 years. Now you might want to also know how much money is going to be in the account at the end of the 4 years. And if you wanted to know that, you'd have to remember that if you earned $120, you started out with $500, so the amount in the account is actually the sum of those numbers. So the principal plus the interest gives you the total amount in the account. That $620, or the total amount in the account, is sometimes called the accumulated value, and the letter capital A is sometimes used for it. But quite often, we want to think of that as the future value. That's the value of the account sometime in the future. So to summarize this, I equal PT gives the amount of interest for a simple interest account. But if you take P and I and add them together, you get what we sometimes call A, or you can call it the future value, and we'll be doing that some later. And that's simply the principal plus the interest. Now, if you think about it a minute, the interest I is equal to PRT. So if you take PRT and put it in place of I, and then factor out the common factor of P, you'll get another variation of this formula, which gives you directly how to get the future value directly. So capital I gives you the amount of interest in the account, the simple interest account. Capital A, which is the future value, takes you directly to how much money is in the account, the principal and the interest together. And again, as I said, that capital A is sometimes called the accumulated value or future value of the principal, or the amount you put in the account to start with. Now, if we go back to that previous example and change the question, instead of asking how much interest will the deposit earn in 4 years, and if we ask how much will be in the account in 4 years, we've already figured that out by just taking the original amount and adding the interest. But I want to show you that you can also go directly to the answer by using this formula. And I don't want to belabor it much, but if you just go directly to that formula and plug the value of the principal and the interest rate written as a decimal and the time written in years, plug those in, we'll get 0.06 times 4 is 0.24, and if you add 1 and 0.24, you get 1.24, and then if you multiply that by 500, you'll end up with the same $620. So it's just another way of showing you that you can go directly to the amount in the account by using this formula, or you can calculate the interest and then just add it back to the principal like we did the first way we did it. So it's the same answer either way. You can also use what we've learned so far to look at simple interest loans. In other words, instead of putting in an accounting earning interest, we can also borrow money using simple interest loans. So this time we're borrowing instead of depositing. These calculations are going to be simpler than what we're going to do at some point later. We're going to be talking about compound interest loans, which are actually the more common loan. But right now we're doing simple interest loans, and they're going to be, as the name implies, simpler. The best way to think about this, I think, is just by doing an example. Suppose we have Angela. She's got a 5-year simple interest loan of $6,140. At an annual interest rate of 10.45%, how much interest will she pay? Remember, this is a simple interest loan, so we can calculate using I equals PRT. The principal is $6,140. The interest rate is 10.45, so as a decimal, you move the decimal point 2 places to the left, and you get 0.1045. The time is 5 years. And if you plug this in the calculator, you get 6140 times 0.1045 times 5 equal, and you get 3208.15. So this $6,140 loan will cost Angela $3,208.15 in simple interest over a 5-year period. That's a lot. That's over half of what she borrowed. As I said earlier, most interest-bearing accounts actually pay compound interest, where the interest earns itself. The simple interest stuff doesn't show up in the consumer market as much. To calculate the amount of interest earned in a compound interest account, we have to know how many times during the year that the interest is paid and added back to the account. Remember that visual example I gave earlier, you're adding the interest back to the account, but you can choose how often that happens. That number of times per year is called the compounding period. And there are some common compounding periods. For example, annual means you compound once a year. Semi-annual means you compound twice a year. Quarterly means you compound 4 times a year. Monthly means you compound 12 times a year. Weekly means you compound 52 times a year. Daily means you compound 365 times a year. The formula for accumulated value, or what I like to call the future value of a compound interest problem, is given by, it's more complicated than the simple interest, but it's still very manageable. It's A equal P, the principal, times the quantity 1 plus I raised to the NT. Now, what do these letters mean? A, we've talked about before. Capital A is the accumulated value or the future value of the account. P, again, we've talked about, is the principal or the present value of the account. Little I, as opposed to capital I, little I is the interest rate per period. And the way you figure it is you take the annual interest rate, which is R. Remember, we said sometimes that's called the APR. And divide it by N, which is the number of compounding periods per year. So, for instance, if your interest rate were 6% annually and you were compounding semi-annually, you'd take the 6% and divide by 2, because semi-annual interest is twice a year. So this little I is the interest rate per compounding period. And finally, T is the time, and again, it has to be in years. So using this, we can answer the question about finding the accumulated value in an account paying compound interest. So for example, let's say $2,000 is deposited in an account that pays 4% annual interest and is compounded quarterly. The question is, how much money will be in the account after 3 years? Well, it's compound interest, so we use the compound interest formula. And again, capital A is the future value. That's the amount that will be in the account later. In particular, how much will be in the account 3 years later. P is the principal or present value. That's $2,000. Little I is the interest rate per period. So you take the annual interest rate and divide it by how many times a year the compounding happens. Well, the annual interest rate is 4%, and you're compounding quarterly, and quarterly means 4 times a year. So you're going to take 0.04 and put in for little r, and then divide by 4 because quarterly means 4 times a year. And that comes out nice. Little I comes out to be 0.01, and that's the value that goes right here. The only thing we haven't put in is the time. Time is in years. In this case, it's 2 years, so you plug in 3. 4 times 3 is 12, and you calculate. Now, my suggestion with this type of calculator is pretty much to start on the right side. You want to calculate this quantity first. And to do that, start on the inside of the parentheses and add 1 and 0.01. So you're going to do 1 plus 0.01 equals, that comes out to 1.01. With the number in the calculator, now you just need to raise it to the 12th power. The power button, as we've discussed, is that x to the y. So you press x to the y, and then you type in 12, 1, 2, then equal. And when you do that, you'll get 1.12682503, and you're going to multiply that by the 2,000. 2000 equal. Notice I did the entire calculation in the calculator. And that's the best way to do it. So you'll end up in that account after 3 years, $2,253.65. Let's do another. In 2017, John's salary is $50,000. If the inflation rate is 2.5% annually over the next 5 years, what would John's inflation-adjusted salary be in 2022? You can use this same compound interest formula just to answer a question about salary inflation. It's the same idea. John's earlier salary is like the principal in an account, and John's later salary is like the future value, the A, in the compound interest formula. So once you think about it that way, it's pretty obvious that you're going to have to calculate all these quantities, and you might as well start with little I. Little I is the interest rate per period. You take the annual rate as a decimal, and you divide it by n, which is the number of compounding periods. And if we're doing this annually, the compound period would be just 1. And 2.5 as a decimal, you move the decimal 2 places to the right. 2 places to the left, and you get 0.025, and annually means you divide by 1. So little I is simply 0.025. And then similarly, the earlier salary is like the principal in the account, $50,000. You're doing it for 5 years, so T is 5, and we've already said that N is equal to 1. 5 times 1 is 5, and 1 plus 0.025 is 1.025. And again, you do the same thing with the calculator you did before. I'm not going to show it again, but you're going to start here and use the button to calculate this quantity and get 1.131408.213. You do need to practice this. And once you get that number, you'll multiply it by 50,000, and that'll give you $56,570.41. Practice doing that entire calculation in your calculator. Now, I do have a question for you. Why does that n matter? If you think about it, it's pretty obvious. When you compound more often, you put the interest back in more often, the account's going to earn more interest. And that means people can, when I say people, I guess mainly I mean banks, can fool you with an interest rate if you're not careful by conflating the compounding period between accounts. So in order to combat that, we have something called the APY, the annual percentage yield, or I usually call it the effective rate of an investment. It's the actual interest rates you earned in a single year that accounts for the different ways to compound. It levels the playing field. You can compare a quarterly compounding to a monthly compounding to a daily compounding, and you get a rate that's apples to apples instead of apples to oranges. And that formula, the APY formula, is very simple. You just take the interest rate per period, which is R divided by N, add 1 to it, then take that quantity to the nth power, and finally subtract 1. And if you want to write it as a percent, in other words, that calculation here gives it to you as a decimal. If you want it as a percent, which you typically do, then you've got to multiply it by 100%, and that changes the answer to a percent. Let's do a couple examples. The first one says find the effective rate for an investment with a 3.5% APR compounded quarterly. First of all, you write down the formula, and then you plug in the values. We've practiced this before, so you've got 3.5% written as a decimal, it's 0.035. It's done quarterly, so N is 4. And at that point, you just do the calculation. Now here's something I hope you've noticed and handled well in earlier problems, and that is occasionally you get something in your calculator that looks rather odd. In this particular case, if you take .035 and divide by 4, what this calculator shows is 8.75 and then a superscript of -0.03. Now that's the calculator's attempt to do scientific notation, and all it means is that you take the 8.75, and because this is a -3, you move the decimal place 3 places to the left. 1, 2, 3. That means you've got to add 2 zeros. And so you actually get 0.00875. If it were a +3, you'd move it to the right. But you have to get used to the way the calculator shows numbers when they put it in scientific notation. The sign plus or minus tells you which way to move the decimal place. Negative means to the left. And the number itself tells you how many spaces to move the decimal place. So in any case, we end up with 0.00875 here, and we're going to have to add 1 to it and raise it to the 4th power. So if you add 1 to it, you get 1.00875. Now you have to raise it to the 4th power. So I've done this with the calculator on screen, but at this point you need to practice it yourself. You use the power button and use the 4th power, write the base, hit the power button, type in 4 and hit equal, and that will then you have to subtract 1 from that. That will give you 1.035462061. You have to subtract 1 from that, and that gives you 0.035462061, and then you have to multiply it by 100%, which has the effect of moving the decimal place 2 places to the right, and that gives you 0.5462061%. If you want to round it, say, to the nearest hundredth, the problem will tell you in general how to round it. But say we want to round it to the nearest hundredth, then you go to here and notice that the decimal, the digit past the hundredths place is 5 or larger, so the 4 rounds up to a 5. So the APY is 3.55% to the nearest 100%. Simple enough. Let's do this one. Find the effective rate for an investment with a 3.5% APR compounded. What you need to think about here is this is exactly the same problem. The only thing changes is that the n being 4 up here is going to become daily, which is 365. It's the only thing that changes. So I won't belabor this, but everything is the same as in the previous calculation except the 365 replaces the 4. And when you divide 0.035 by 365, you're going to get this long decimal. You have to add 1 to it, and then you're going to raise it to the 365th power. And that gives you 1.035617971, and then you have to subtract 1 from that, and then multiply that by 100. And you will end up with 3.561797%. And again, if you want to round that to the nearest hundredth percent, you'll look here and notice that 6, because that number 1 is smaller than 5, stays 6, and you'll get an APY of 3.56%. Practice, practice, practice. Use your calculator. Practice using your calculator. Go back and do these until the motions seem fluid, and you can do these consistently without having to back up and correct a mistake. Just keep practicing.